Hi everyone, welcome to another Math Club talk. Today we have Bikram Halder, and he's interested in probability. And the topic for his talk is he will present a proof of Cayley's formula via Poisson Branching process. Over to you.
Thank you. So before going into actual proof, we want to understand, we will get into some machineries that needed for this. What is Cayley's formula? Uh, that the number of spanning trees of the complete graph Kn is equal to n to the power n minus 2. Or equivalently, we can say the number of labeled trees on a n-vertex graph is n to the power n minus 2. So at the end of the talk, we'll prove this. Before going into this, I would introduce first the what is branching process and its random of perspective, which is needed for proof. So let's go. Okay, what is branching process? It is the simplest possible model to model a population of maybe bacteria, particles, or whatever. What we do here, that we start with a, let's say, bacteria, and it gives birth to a random number of same type of bacteria, let's say, and we take this number as random, okay, and after giving the birth, it dies out, and then these childrens get active and gives birth to other bacterias. Okay, now how to analyze this? We say at generation 0, let's say t equal to 0, time 0, there is just one bacteria. Then at time 1, this gives birth to say 4 bacteria, and then time 2, these two gives birth to some other bacteria. And as we have said, we put this number as random. Also, if for each one of these bacteria, we take is identical. We take all these numbers as identically distributed. Say at time 0, say this is x01 random variable. For the number of children at time 1, it is x11, it's x12, it's yes, let's say it gives birth to only one children. Okay, yes, psi pi equal to number of children of the ith say particle at time t, and we take all these xti to be IID some non-negative integer random variables, of course. Otherwise, this doesn't make sense. Now, uh, what we want to ask here first: uh, does this population survive forever, or it gets extinct? And what is the chance it gets extinct or survive forever, whatever? So let's define this Zt to be number of offspring total. Okay, so total number of offspring. Uh, generated at time t. So that can be written as sum of xti. I mean, we are counting only the number of offspring that generated at t. So this will be 1 2. How many generated uh, there? Yeah, zt minus 1. So, when will it get extinct? So there should exist a, okay. Hmm? Oh, sure, sure. So when this I mean, this population gets extinct, so there should exist a t such that this ct equal to 0. So we want to compute this probability. Say to be eta. Then an interesting result is survival extinction. It will get extinct, that means it equal to 1 if the mean of the random variable that we choose for this offspring distribution, that means the number of children that goes for every part generated for every particle, that that is less than 1. It has lesser probability if this expectation is greater than 1, and 3 again it will get extinct if expectation of x equal to 1 as well as probability that x equal to 1 will be lesser than 1. This this theorem has another formulation in terms of probability generating function, but before that recall what is that. Say PGF, it's just a generating function, as you have studied that moment generating function and cascadic function also, it's the similar thing, but this is defined for non-negative integer valued random variables. So gx of s is defined as expectation of s to the power x. That means it is s to the power r, probability x equal to r equal to 0 to say infinity. So you see that this is actually looks like a generating function. This is, and uh, we can check its convergence for from 0 to 1, or is in say 0 to 1, this actually converges. It's easy to check. Jx is convergent. Now look at this. Gx of 0, what is this? It's probability that x equal to 0. Look at this. Gx dash of 0, this is probability that x equal to 1, and again if you go like this, you can see that the rth derivative of the generating function evaluated at 0 is probability x equal to r times r factorial. So as you can see, for any non-negative integer value random variables, this gx is well defined, as well as uh, uh, as well as uh, this is unique, because if you take two different random variables whose gx is same, evaluate like this, taking the derivative and evaluate at 0, you will get the same random variable. You can equate this. So, oh sure. So the alternate formulation is this: uh, this eta is the least solution in 0 1 such that the solution of gx gx of s equal to s. X is the that Austrian distribution. So this is quite an interesting result, but we don't need this. I am just stating this for the test. Okay. Run this. Now we go into the random walk perspective of this. So what we did in the branching process, we tried to model it generation wise. That means at time t, all the children generated before this, they produces the children. Here, what we do, instead of doing that, we do that leaf wise. Okay. So let's say at first we have one particle, then it generates a random number of particle, give it and this number gives this x1. Now we choose any of this, and this particle generates another other particles, and then we choose any of these leaves, they generate some other particles. So let's say this generates some x2 number of particles, this generates some x3 number of particles, and so on. As you can see, this also generates the same branching process, but it goes differently. So now we have same question of extinction. That means when this gets extinct. So whenever uh, this one particle generated, and if it gets extinct after that, before generating any particle, and this happens for all the leaves, then of course the population gets extinct. So say, so what we want to do, at each time, first we model like this: at each time t, we count the number of, say, whoever can generate the particle is active and others are active part. So say at time t, this is st. Okay. Now then, what is at time 0? This is 0 will be 1 because there will be one particle. at sorry okay at time 1, this count will be the number of particles generated at that time. So it is x1 plus the number of particles that generated before, that is 0, and the parent that died, minus 1 because of that. So as you can see, at time t, at any time t, this will be xt plus st minus 1 minus that parent who just gave birth. So for this to compute, like what will be the probability of extinction when will it get extinct? Say we would like to know when this st will be 0. Okay, so that there is no active vertices at that time. So let's take t to be the this t such that st equal to 0. So what that means? Look at this. This is xt plus xt minus 1 plus st minus 2 minus 2, and as you can go along, which will be nothing but x1 to x1 up to sum of x1 up to xt minus t minus 1. So that means this will be infimum of t at x1 to xt equal to t minus 1. Now there is a result that this on the distribution of this t, and one thing to note that uh, this t is nothing but the total connected component form after formed up to that extinction. That means this is the total number of progeny of that BP, of the branching process, and the result is equal to 1 by n times probability up to x n equal to n minus 1. As we are doing for Poisson branching process, but if we take all these exercises to be Poisson, what will this become? Take all of them to be Poisson, say x or lambda, then what does this become? 1 by n probability. Now by additivity of Poisson, it gets sum at the parameter, so this will be Poisson of n lambda equal to n minus 1. So what does this become? L2 e to the power minus n lambda times n lambda whole to the power n minus 1 divided by n minus 1 factorial. Then what is this? E to the power minus n lambda by n minus 1 factorial time n to the power n minus 2. Can you see n to the power n minus 2? Okay, so we need to get rid of this term only somehow. Now we go to the main proof. Okay, so we introduce something called family trees. This is nothing but a new labeling given on the trees. So what we do, we fix a root for a tree, we fix a root phi, and then like label its descendant, say the three descendant or neighbor. Okay. 1, 2, 3, and their descendants as 1, 1, 1, 2. Say this has only one descendant, so 1, 2, 1. So it has three descendant, 3, 1, 3, 2, 3, 3, whatever, like this. So in general, what we do, we label it as this, label the root as phi, then take the descendants of this as 1 to d of phi. Okay, where d of x equal to the number of descendants of x, and their descendants as some, say 1 1 up to 1 of 1 of do, and this d of phi 1, d of phi decompose 2 times phi. Okay, just like this. It's just a new labeling on the trees. Okay, this labeling is called Ulam Harris representation. Now let's look at this. Okay, say we take a branching process with offspring distribution in as UI1, Poisson 1. Then some let's say tau be a random variable which is on trees that generated by this offspring distribution. Then we have a tree generated by this, or say this. We label it using, okay, label using Ulam-Harris labeling, that thing, and we try to compute its distribution. Since the number of children of each of the particles is identical and independent, we can break its product like this. Okay, probability that, say, at each particle, okay, the number of each particle is like this x w, where W is the word of that vertex, equal to the number of children, that is D of W in that tree. So because these all are identical as Poisson 1, it will be e to the power minus 1, 1 to the power of W by D of W factorial. Okay, so what this becomes? This becomes okay, number of e to the power, whatever the size of the tree, time by product of all the dw factorials, w in tree. So okay, we need this result to use. Now uh, let's say we have a branching process, and okay, let's say it has a tree like this, and we condition on the total number of progenies that generated in the whole branching process. On say, so what will be that? Let's say we condition on n, so that we get in vertex, of course, and we take the labeling of this from the set 1 to n. For the root vertex, we always take 1 as this label, and for others we label them uh, from okay, label them from 2 to n uniformly at random with replacement. Sorry, without replacement, whatever is what I mean. Without replacement, so that you don't give to what is same level, of course. Now let's say we want to condition on this and compute the probabilities. Okay, let's say we fix a label using this of this label L, and consider the tree, family tree, that means family tree means the labeling using that Ulam-Harris representation of a tree. So let's say T tilde L if T can be given label L, and we want to compute how many family trees are there such that can receive label L. What is this? So look at a family tree. This is 5. So this has 1 to D of 5, and descendants as is 1 1 and whatever. Now fixing the root, of course, if you permute the descendants, then the tree remains same, but the labeling is different. So that will so then what does that become? I mean, what is the total number of such labeling are there with fixing this time? This is nothing but d of w factorial such that it belongs to t. Okay, because we are fixing L and I'm counting the t. Let's say d of w to be degree of w minus 1 for w not equal to 1. and this is degree of W for W equal to 1. So that will remain the same actually. This one L, but in this course we are counting more number of trees of more number of family trees. So then we divide by those label trees, uh, this those label trees, number of those label trees, such that it can be given that labeling as well as this is isomorphic to L. So, and yeah, then this number of all the family trees becomes like this. Okay, I'll make this. Now we have to compute what is the chance that a family tree receives a labeling L, receives label L. Okay, so what we are doing, except the root, we are giving labeling to rest of them uniformly at random from the set, okay, 2 to n. So what will be the favorable number of cases? That is nothing but the size of the tree minus 1 factorial. Now, sorry, what will be the total number of cases? That's size of the tree minus 1 factorial. And what will be the favorable cases? That's precisely the number of all those label trees that's isomorphic to L and can be given label to T. So it becomes L of L. Now, okay, now let's compute that a tree uh, is given, this L is a random variable on the labeling of trees on n vertices. Let's say, then let's compute this probability. What this becomes? That's nothing but you can sum this on all those trees that can be given label L. Probability that uh, T is a family tree and T receives label label L. That is sum over the trees that can receive label L. Let's decompose it. Given T receives label L times probability that T, okay, receives label L. Then okay, and this probability becomes, okay, I am writing again because it is not visible. Now look at this term. Does this term depend on L? No. So you can remove this and take their product. That means this is, as we have computed here, to be e to the power minus model divided by, yeah, product of all dw factorials, w will say L by our this convention, times the probability that T receives a level L, that would be L of L divided by model minus 1 factorial. Then as you can see, this term doesn't even depend on T. So we take the total number of trees that can receive level L, E times all this clutter. So then what does become? Let's plug into this. Times, okay. Now what cancels? This and this, also this and this. So what remains? B to the power minus model divided by minus 1 factorial. Okay. What should, okay. I can use this. Hmm? No, it is needed. Oh, this part. Oh, thanks. Hmm. Now let's go to the main thing, that we are giving a level L given that the total number on the total number of vertices of n. Then what is this? This is just the conditional probability equal to L, comma, total number of vertices equal to n divided by probability of total number of vertices equal to n. So as you can see, the size of L, we have already assumed that it is n. Then we can remove this part and get this. So what is this? As you have computed there, this is e to the power minus model divided by model minus 1 factorial. Oh, let's write n, not model, times, what is this? This is the total number of progenies that generated, the total number of the probability that total number of progenies is n. So what is this? This is e to the power, here because we are considering Poisson 1 process, so lambda is 1 minus n to the power n minus 2 divided by, okay, n minus 1 factorial. So what that becomes? 1 by n to the power n minus 2. So for any labeling n, this happens. I mean, of course, on the n vertices. So as you can see, because this is true for any labeling L, so this probability is uniform. That means L given we are working on any number of vertices n is distributed as uniform n to the power n minus 2. So the total number of trees, label trees on n vertices would be n to the power n minus 2. That's the proof. Okay, any question? Oh yeah. One thing I didn't plan but I want to do. Okay. For a graph G, uh, define its adjacency matrix uh, Aij as 1 if I is a neighbor of J and 0 otherwise. And Bij to be its all the degree sequence, the diagonal matrix with the degrees of all the vertices on G. Degree of I. Let's say equal to 1 to 1. And take this matrix L to be T minus A. Okay. Now, if G is a complete graph, what this A becomes? So, every vertex is connected to every other vertex. So, as you can see that this matrix has zeros in the diagonal because of course no vertex is connected to itself and 1 in the rest of the part. Okay. And what is D? D becomes the, because every vertex is connected to every other vertex, that means n minus 1 vertices in total. So everyone's degree is n minus 1. You can write it as n minus 1 in the diagram. So for Kn, this becomes n minus 1 times In minus, okay, which is, let J take the all one matrix, that means all entries are 1, then it is just subtraction of J minus I. Now, how does this look like? This just looks like n minus 1 in the diagonal and minus 1 everywhere else. Okay. How many minus 1 are there? N minus 1. Here also it's symmetric because. So as you can see, the row sum and column sums are 0. So this matrix has determined 0. No use of it. So what we do, we remove the last row and last column and consider this block only. This has n minus 1 many ones, of course, in the diagonal, and then minus 1 rest. So consider this. Then we delete the nth row and nth column. That would be n minus 1 times In minus 1 minus is the same Jn minus 1 minus In minus 1. Now, what? No, n minus 1. The diagonalities are n minus 1. Okay. Now, we call the projection matrix, like Pn, that's what 1 by n, 1 by n, and this is the projection matrix. So we can write Jn minus 1 to be n minus 1 Pn minus 1. Okay, and identity matrix can be written as the sum of projection and its perpendicular operator. So what this becomes, this is n minus 1, okay, plus 1 of course. So this n times p, let's write p, not anything else, let's p transpose, sorry, p part minus n minus 1 p. Okay, then what it becomes, this is p plus n p part, right? So this is one projection, this is another projection, and recall from linear algebra that this is nothing but the spectral decomposition of this L of kn. So then what the determinant becomes, okay, how many n's are there, this p, okay, okay, and this p, what is the rank of this p, because p has all entries are 1 by n minus 1, the in all the rows, all the columns are identical, so its rank is 1. And so, and because we are working in n minus 1 order, its rank will be n minus 2. So as you can see, what are the eigenvalues of this, then 0 one time and n minus 2 times, fine. Oh, 0, sorry, 1, what am I writing, then what will be the determinant of this, determinant of, let's say, L, removed L equal to n to the power n minus 2. So that's also a theorem. If you remove the any row, any column from this L matrix, that determinant become the number of spanning trees of the graph. Okay, you can look at it. You made this. You will also see this later in your graph theory course. Any question?
Okay, thank you, Bikram. So we'll have a applause for you. No more questions? Okay, that's it then. Meet you next time.